Good evening or morning, as the case may be, everybody. My name is Darren Lipomi, one of the organizers of this symposium. I work at the UC San Diego Department of Nanoengineering and Chemical Engineering program. And I have a couple of my co-organizers as the moderators of this panel on haptic materials and haptics for VR and AR. And they are Ben T from the National University of Singapore and E. Menguch from Facebook. And what I think we should do first is go around and give a short introduction to all the moderators and the panelists. So let's start with Ben.
Hi, well, welcome to this symposium, and it's been really fun organizing it together with Darren, who did significant amount of the heavy lifting. I must say, thank you, Darren, and also thanks to the panelists for joining this. So I'm Benjamin T from the National University of Singapore, and briefly I work on sensors and soft materials, and generally very interested in haptics. And I think that moving forward, the human-machine interfaces will probably change a lot. And I think that we are the emerging phase of such technology. It's been taken some time, but I think that we have a lot of tools now that we can advance haptics. So thank you.
Great, thanks, Ben. Yeet.
Hi, thanks again, Darren. And let me first echo Ben in thanking Darren for doing an immense amount of work. It always amazes me to see just like how much effort is needed to herd all the cats. And Darren did a great job of cat herding today. So thank you, Darren. And so my background is in mechanical engineering and got into materials science a little bit as on the side, working as a postdoc in soft robotics, but now I'm a research science manager at Facebook, where haptics is a big part of how we anticipate humans will interact with virtual and augmented worlds to make things more natural. So I'm very glad to see that there's a lot of intellectual curiosity and energy here. So I look forward to seeing a lot more in this webinar.
Great, thanks, Heat. How about Charles next?
Yeah, thanks so much for organizing and having me here. I'm Charles Stong. I'm an assistant professor at the University of Delaware in the Department of Material Science and Engineering and Biomedical Engineering. And briefly, our lab works on measuring and controlling mechanical forces in biology, ranging from cells all the way up to the human sense of touch. So more relevant to the panel here is we use tools from material science to develop new ways to create tactile sensations or develop new types of materials that can reveal how touch works.
Great, thanks, Charles. Ed?
Sure, I'm Ed Colgate. I'm a professor at Northwestern University and have been in this field of haptic interface for a very long time. The first chunk of my career was on essentially robotic devices, force feedback devices. And then I did a few other things. And then for the past 10 to 15 years, I've been working on what we call surface haptics. So basically enabling people to feel rich haptic sensations on flat, usually rigid surfaces like touchscreens. And I will say that in the last year or so, it's really dawned on me that we need to move beyond that. We need to be thinking well beyond that, and that materials and the sorts of challenges that many of my co-panelists here are thinking about and at the forefront of developing is really the future of the field. So I'm excited to be a part of this. Thank you for inviting me, and I look forward to the discussions.
Great, thanks, Ed. Fabrizio?
Yep. Hi, everyone. I'm Fabrizio Sergi. I'm an assistant professor at the University of Delaware in the Biomedical Engineering and Mechanical Engineering department. My work is mostly focused on human-robot interaction, and specifically on human-robot interaction in the context of neurorehabilitation. We've been developing robotic devices that can support motor function, like replacing the function of a human therapist. And we've also been trying to use robotics to understand principles of motor control using a combination of robotics with imaging techniques. So I see myself as more of a system integrator, and I've been interested in seeing what potential new materials can afford to our field and try to bridge the link between materials and application of these materials in human-robot interaction. Thanks so much for inviting me. I'm excited to the discussion.
Okay. Thanks, Fabrizio. Laure?
Hi, everyone. Thank you to the organizer for having me here. It's a really exciting panel, and I really look forward to the conversation today. My name is Laure Kaiser. I'm an assistant professor at the University of Delaware in the departments of material science and engineering, as well as chemistry and biochemistry. My training is organic chemistry. I'm a synthetic polymer chemist, and so I'm interested in designing and synthesizing new materials to interface with the human body. My group works in the area of bioelectronics. We make stretchable and soft electronics that can be interfaced with the human body, either directly or indirectly for implantables and wearables. And we're gearing a little bit towards actuators also and stimuli responsive materials to study and trigger tactile sensations.
Okay, thanks, Laure. The first question I would like to ask is, how can we think about combining actuation and sensing? Because we are often working in several of our talks were in a medical context, where we have a haptic robot or haptic appliance where sensing has to be integrated into the actuation component. But even in surface haptics, you need to be able to sense the finger, but also provide feedback in real time. And I'm wondering how you think about combining these functionalities. And you can take this from a materials integration standpoint, or look at it from the standpoint of combining stimulus and response with or without the use of integrated circuits. And how do you think about that? And we can start with well, I don't want to ambush you. So if anyone has something they'd like to say, by all means, you can speak up. And if we need to do this in a more formalized way, I can certainly call on our panelists.
All right, I'll start because I'm the old guy here, so I'll start and make it easier.
Thanks.
I'll try to say some provocative things that the rest of you can jump on. So it's a really, really good question, Darren. Those who've worked in haptics think a lot about the fact that haptics, perhaps uniquely among the senses, is bilateral. So to perceive things through touch, we must touch them. So we must take an action and then feel through our senses a response. And very often that's an energetic interaction. There's very non-negligible amounts of energy flowing between you and the world that you're touching. Not always, but very often. And so given that it's bilateral, what's happening is happening in this kind of closed loop. And so the systems that we end up building are these closed loop systems, and to make them work properly, you end up with all the same sort of problems that anyone ends up with when they're designing a closed loop system. For instance, stability, performance depending upon sample rate, the latencies, things of this nature. So it's usually quite necessary in haptics to think about sensing and actuation together from the get-go. I know a lot of people tend to like the notion as they think these days, especially about bringing in soft robotics. Well, maybe the sensor and actuator can really be, analogs that can just be the same thing, run in different directions. And usually that's not how things end up. All right. Usually actuators are really tailored to their power regime, the fact they have to do mechanical work typically, whereas sensors are meant ideally, right, to sort of be energetically as neutral as possible and to affect the behavior of the system as little as possible. So usually we end up with different either different technologies or different scale or application of the technologies for sensing and actuation. Whether that will continue to be the case as we move into the future, we're powered by new materials and soft robotics ideas, I don't know, but I put my money on that it will probably continue to be the case for pretty fundamental reasons having to do with just the scale of the signals and the power.
Yeah, I think I like the way that Ed has framed this, and it's definitely definitely the one sense that requires this coordinated investigation of action and perception, right? Definitely from an analysis standpoint, we can only study haptics and sense of touch in this framework. Going more into what it means to include this capability into, you made the example of medical systems, and in this case, we may be talking about restoring sense of touch through prosthetics, right? So, well, in that case, then I will first start by saying that it's true that people look at these two problems separately, right? In most cases. And I wonder whether, maybe for some application that is necessary. Indeed, the way to restore the link between perception and action in a prosthesis on the actuation side requires very different, poses very different constraints as compared to what you would need to then restore the sensation of touch back, right? And at that point, you have to worry about problems like stimulation at the neural or peripheral level, and that may be a very different problem, right? So I agree that probably integration between sensing and actuation is very important for haptic systems in general, but I also think that in that case it will depend a lot about the application that we are talking about. So that's
Yeah, and to kind of take a different perspective from what's been raised, it's kind of some of the ways I think coming from a materials perspective, and not to say this is all materials perspective, but one of the things I think about is, how you have this problem of like someone's going to touch an object, and you may not necessarily know how they're going to touch the object, and that's going to change how something feels, both in terms of literally what are the forces being generated because someone's pressing harder or sliding faster, but also what are they expecting, right? Like you're pressing hard yourself, you're expecting a certain kind of feedback as you press harder and as you press lighter. So kind of one of the ways I think to address this is, so how can you program materials to then respond instantaneously, right? So in this case, the sensor is kind of embedded into the material and the way the material responds. So one of the advantages of this method is that it's instantaneous, is that there's no delay between the sensor and the actuation. I don't think this is as rational necessarily to design, because it's not like we can say we want to generate this force at this exact time. We kind of have to program, well, if someone presses in this manner or presses in another manner, here's the forces we can expect the material to generate. So I think that's a different system, but it could be one way to kind of bridge this actuation sensor gap.
Great, thank you all. I should mention that if any of my other any co-moderators have any questions to jump in with, by all means do. So Ben or Yeet, by all means, this is your panel too.
Sure, thanks. Yeah. Thank you, Darren. Ben, go ahead.
Oh, okay. So thanks. I think those were really very interesting thoughts around haptics and some of the limitations. And I guess there was a mention about latencies. And for humans, we typically operate, in, I would say between about 10 to 50 milliseconds is the response time. So do you, to the panelists, are there any challenges right now trying to achieve that kind of latencies required to actuate at the resolution needed for fine touch discrimination? And what technologies are probably the most promising currently?
Maybe I'll start by answering that one. it's really a challenge because you can have things that move really fast, but require a lot of power. And then you have things that don't require a lot of power, but are much smaller and bulkier in some cases. And so there is kind of a disconnect in materials science and materials chemistry, maybe that can be addressing this. The pneumatic system and the inspiration from soft robotics is great, but for fine touch, it's very, very difficult to miniaturize those systems. And I think we are making good progress in terms of like kinesthetic, but for fine touch, it remains really a challenge. Even miniaturizing things for fine touch is really, really hard, even with electroactive actuators and other like electrostatic or electroadhesive systems. And they require a lot of power, but they're amazing, but there's like trade-offs and all of those. And so they think there's still a lot of work to be done in this area.
Yeah, and I should mention, I think Tanya has joined us too. So, and I know she's an expert in all this too. So, but I'm gonna go ahead and chime in. You mentioned the 15 milliseconds ban, and so it's interesting. And back in the day when a lot of us were working on this force feedback haptics, the rule of thumb was always 1 millisecond. And quite frankly, through the years, it's sort of the numbers only dropped. And the reason for that is, again, this closed loop nature of things. If you, and this is really kind of kinesthetics to Lara's point, but if you run into something that's hard, then the forces can change very, very rapidly, right? And so to simulate that, and by the way, and I think this is something really important to understand, is that like I'm very, very excited about all the incredible things that are happening with kind of bringing soft robotics and soft materials ideas into haptics. But think about what we're often trying to do, say in virtual reality. We're trying to emulate interaction with the world, which is mainly full of pretty rigid things. And so when you interact with rigid things, the timescales can become very, very compressed. So very often the challenge is to achieve much, much lower latencies than say 15 milliseconds. Now this is less true when we get into the tactile range than in the kinesthetic, because it's not closed loop to the same extent. You don't have the same stability issues. But you still find, I know a little bit in sort of the commercial world when people are trying to build really crisp feeling vibrotactile actuators, or in the work that I've done in surface haptics, you're still trying to push that latency down, typically below 10 milliseconds in order for things to really feel right and feel crisp. So kind of rule of thumb in my mind, which is very context dependent, but sort of in the tactile range below 10 milliseconds and the kinesthetic range below 1 millisecond.
Great, thank you.
Yeah, I like the discussion on latency, and because as engineers we always try to improve our systems and to make them more robust and faster. And I also, I wear kind of two hats. The other hat is of, using robots to study neuroscience. And I've been really amazed when I study how instead it's not the acuity of sensors, nor their refresh rate, nor the speed of a closed loop cycle that we really need to, where humans, for example, excel. The time between we do a lot of paradigms where we stretch muscles, and the fastest spinal loop is on the order of 20 milliseconds from muscle stretch to what's called a short latency response. And so that's 20 milliseconds, and it's just going through the spine. And if you look at loops that instead cross the motor cortex, then it will take more than 50 milliseconds. And a voluntary contraction, if you do the 100 meters and you have 100 millisecond delay time, which is assumed from the acoustic stimulus to the response time, right? So humans do not really excel in having incredibly, in the acuity of their sensor, not of the speed of response. Yet when we develop engineered system, we really need to achieve a sampling rate that are much faster, because otherwise our systems become unstable. I've always been fascinated by this observation and wondering if whether our biological systems may have evolved in a way that there is a lot of mechanical intelligence in the way they are built, and in the properties of the muscles and of the fingertips that are in contact with the environment, and whether that may be instead a different pathway that will allow, improved performance of, in this case, soft robots or human interacting robots. So just to chime in on the issue of refresh rate of sensors, which I agree should be improved, but maybe that's not the only path.
Yeah, and just to kind of go off on that point, I think something about the only path, something Ben mentioned is this idea of recreating fine touch. So there's different areas of haptics, different kind of goals of recreating their bulk motion or fine texture. So how can you tell two objects apart just by stroking them or touching them? In this case, I think that, like currently most actuators are based off of a physical means, right? Like they'll make a bump, or they'll make a ridge, or they'll make a groove. And here I think is where there's a lot of opportunity for material scientists to think of new systems and new ways of changing the surface chemistry, using different materials phenomena. And these actuations can be fast because you don't have to have as large of a motion. How can you rearrange the outer layer, the surface layer, to present, something hydrophilic, hydrophobic? Those are just examples to really enrich in the experience. So can you layer this on top of this kind of like physical way of recreating features, recreating roughness, and then change the surface chemistry to add another layer of this fine touch aspect? So I think there's some lower hanging fruits in terms of material systems which can work, but there's definitely interesting challenges as well. Finding these lower limits if we set our kind of goal in mind, our engineering parameters in mind. What are the materials that can respond that fast, and what is the range of sensations that they can create that's additional to just bumps and physical textures?
Cool. So it's true that most materials that we will come across in our day-to-day lives will be high modulus, they'll react quickly, but our interactions with most surfaces are actually mediated by a thin layer of organic species, whether they are physisorbed from the atmosphere or even if it is an organic solid. The problem is, from a technological standpoint, is that there aren't very many molecular actuators, certainly not ones that are easy to address without producing fairly obviously confounding variables like heat and redox chemistry and this kind of thing. So that's a big challenge with molecular interfaces. I did want to take a quick pause to allow Tanya Morimoto, who is my colleague at UCSD. So we haven't reached the UDEL contingent yet, but there are two of us here. So Tanya, can you take a minute to introduce yourself to the moderators and the panel and the attendees?
Sure. Yeah. Thanks, Darren. I'm happy to be here. And thanks, Ed, for telling me to join in. So I'm an assistant professor at UC San Diego, as Darren mentioned, in mechanical and aerospace engineering and the Department of Surgery as well. And so my research is mostly focused in the sort of soft, flexible robots for surgical applications. I typically, the research we work on is mostly with the snake-like sort of continuum robots that can conform to these really highly curved paths and navigate in these constrained environments. And so I'm interested in designing, new versions of these robots, as well as sensing mechanisms to better understand sort of how are these robots interacting and behaving with the environment, and investigating how can we also create user interfaces that are going to be a bit more intuitive for controlling these types of robots in this kind of constrained environment inside the human body.
Great. Thank you, Tanya. I also want to make an announcement about the way to ask questions to the panel. You can use the chat box either in Zoom, so you can you can send your, actually, I'm not sure if the attendees have access to the panelists, but all the attendees do have access to the panelists using the web interface. So not the Zoom interface, but if you go onto the MRS Pathable site where you logged on, you can go to meeting details and navigate over to the chat function. And a couple of us have just kind of entered some greetings there, so you can enter your questions there, and we'll read them out as the moderators. So I heard the word energy a lot, and energy requirements, energy dissipation. How do you think about energy in a wearable haptic device, in a surface haptic device, in a haptic robot? How do you envision that these devices will be powered? What are some of our goals or performance metrics? How do we think about that? Okay, well, while you have a second to think, Damon from MRS says that participants can send questions on both the Zoom platform and Pathable. So you have a couple options.
I think about energy a ton. To me, when we're using our hands in the world, well, the haptics is sort of, again, I mentioned earlier, kind of bilateral. So sometimes the world touches you and is putting energy into you. A lot of the time you're touching the world, and your muscles are the source of energy for everything you feel. So it's kind of a shame to build haptic interfaces that require a ton of energy. All right. And yet we always seem to end up doing that. And I think a big part of the reason for that is that it takes a lot of overhead to get energy from where you're storing it, which these days is usually a lithium-ion battery, to where you need it, and to convert it to the form that you need it, which maybe is going to be, again, mechanical, certain amplitude of motion, certain bandwidth of motion, and a certain sort of length scale over which you're applying that. And so to convert it from that one form to another form, and to do that in an elegant way that doesn't store a lot of other energy along the way, is a really big challenge. Think about the ways that we typically do this sort of thing, maybe pneumatics, for instance. It's like you get the battery, then you got a pump, then you got a capacitance, that you're storing energy in the air, and then you've got a transmission line, and then something mechanical happens. And it's incredibly inefficient, and, things end up being bulky and inelegant, et cetera. So I feel like one of the really rich opportunities in the space that, again, you folks are in, is to bring the storage and the ultimate application of the energy much, much closer together. I don't pretend to have an idea of how that can be done. I mean, I don't know that it's necessarily a matter of just the newest dielectric elastomer or something like that. Maybe it is. But I don't know that it has to be completely direct. One of the things I like to think about is, we're mostly looking at these LCD displays that have sort of a global energy source and a backlight, and then it's sort of locally modulated. And so ideas like that, I think, are really interesting. But in any event, this challenge of storing kind of only the energy you need and really efficiently getting it in the form you need, where you need it, to me, that's a massive challenge for the field. So I'm hoping other people can explain how they would solve that problem.
Yeah, I mean, before we wait for that type of contribution, I'm going to provide mine, which is not going to be that. I actually was going to respond to unfortunately, to the question, saying that I completely agree. That is really one of the most challenging, aspects of, integrating systems for human application. if you think about how much, energy is required to support human movements, right, in human scale motion, those systems tend to be highly energetically inefficient. And I do think, and specifically, I have, not done a lot of work directly into autonomous systems. And one of the reasons is not because I didn't want, but it's because it would imply so much added overhead to the user. And in our applications of rehabilitation, then we would end up preferring a system that is not energetically autonomous for that reason. What I was going to add is an aspect that we try to go around the lack of efficient energy sources. And for example, in exoskeletons, there are a lot of design methods that allow to support for some of the components of movement that are required. For example, gravity balancing, with springs and compliant elements that offload at least a portion of gravity from the user. For example, an arm exoskeleton that can achieve gravity compensation, or a percent of compensation of the gravity of the arm. It can have already an incredible amount of benefit for a user that can now, there are a lot of neurological reasons why that may be useful. There are also examples of exoskeletons for children that are completely passive, and just with springs, just the fact that they can just keep their hands in a position where they can interact with the world does a ton. And I think that just shows how much a powered system instead could do in so many applications, and how much the field is really suffering from the lack of reliable and sufficiently energetically dense sources.
Great. Alec, sorry, go ahead.
Darren, if you don't mind, I was going to direct the question to Laura, because she does look at kind of a almost autonomous and like combining lots of things and electroactive, which Ed mentioned. So I wanted to hear her thoughts on future of electroactive polymers solving this problem.
Yeah. I was going to chime in from like a chemistry perspective. So like as chemists, we think a lot about energy. Like you need energy to create bonds, you need energy to break chemical bonds. And chemists have perfected the way of using energy efficiently. And so the early methods, everybody was using heat. And so like that's a very simple way. Unfortunately, it's not the most applicable to like human interfaces. You probably don't want to burn anybody with your haptic device. But there are ways around it. There are ways of breaking bond very efficiently using catalytic systems, like lowering the activation energy to like create bonds. You can also use light, which will also like, there's a lot of really interesting like light activated stimuli responsive materials now. Redox systems are really cool because they use very little energy, but now they're limited a little bit in terms of speed because you have to transport ions through like large bulk materials, so it's a little bit speed limited. Conductive materials can address a little bit this like speed issue, and so that's why some of the hydrogel systems have been really popular. But I think there's still a adoption barrier. I feel like there's maybe a little bit of a lack of communication between like chemists making really cool molecules and people putting them into devices. It's not an off-the-shelf material quite yet. It's not our favorite PDMS bottle that we can just use and integrate in our material. But so I think the field would probably benefit from like a close collaboration with scientists working on stimuli responsive materials that have like perfected the control of bonds and chemical structures. So I don't know if I have like a solution yet. I'm working on it, but I haven't found the perfect material yet either.
And Laura, if I can, I think that's very interesting. And yes, there is a lot of potential. And as an end user, again, like someone that tries to integrate this solution into systems, right? One of the challenges sometimes has been the difficulty in controlling these systems. And as we were talking before with Ed, already, you know, standard position control poses some concerns, but when you try to implement interaction control of, you know, a wearable device with the user, you know, as we've heard, there are requirements of controllability that are pretty stringent, right? And maybe that's why we've also, but are there chances, are there options that may also do well under the standpoint of controllability?
Yeah, I think there are options. And I mean, everything we use are electronic devices, right? Like televisions is electricity controlled. And I think that's probably the avenue that we want to take as well, is like electroactive actuators are definitely one way to go. And there are some really good ones out there. They have some challenges in terms of energy, but we can think about ways of designing materials specifically for usability. And that's definitely something my group is thinking about. And I know you know about this project too, but it's like we're trying to make like redox active materials, things that can be addressed with an electric current that would be fast enough to like respond and like change their mechanical properties under an electric voltage. And that would be something that needs to be scalable also, because making thin films is not going to help anybody. We have to be able to like create bulk systems. So there is like a lot of steps before we can apply it in a device. But I think like getting chemists to think about applicability is really good, because otherwise we'll just make our low vials forever and not put it in any device.
Actually, I was going to say, when you were talking about that, I think an additional constraint from some of the work that we do with these surgical robots is the form factor and the size constraint. And that puts a lot of constraints in terms of, you know, how are you going to power any of these sort of components or these materials. If you want sensors that you're going to add along the length of your like very, very thin backbone robot, I think a lot of these concerns become exacerbated in this form factor as well, where I think new materials could definitely help.
So, Laura, could you say a little bit more? You said redox reactions impacting mechanical properties, and I wasn't sure. So, you know, one way we often think about things is, well, we're just trying to generate a displacement or a force. But Charles pointed out earlier that, well, no, you can think more broadly. You can think about changing material properties like lubricity or elasticity or things like that. And so I'm curious, where are you going with this? It sounds very, very exciting.
So what we're looking into is like looking at systems that can change like their degree of cross-linking. So we can make like a polymer that goes from something that is linear to something that is highly cross-linked. And so we can do so using like redox active metal centers that can have like strong like coordination and attachment and creating like really tight cross-linking points. But when you reduce them, those like cross-linking points will like collapse and dissipate. And so that's a concept that people have used in terms of chemically triggering those reactions. So you can use like acid-base reaction to do this, but you can also do it in a redox fashion. And so that's what we're looking at now, is like trying to address those electrically.
Mm-hmm. That sounds very cool.
I wonder if I can jump in with a question from an attendee. So Alex asks, where do you feel that haptic illusions or passive systems fit into the problem of energy? And I wonder if I can tack on an addendum to that question related to haptic illusions. So we think a lot about in terms of creating realistic sensations, so things that really do a good job recapitulating the feeling of an object that you find in nature or in the body or on a screen. But another way to think about it is clarity of intent or clarity of communication. So maybe it doesn't feel like the object, but you know what it is. And I wonder how you think about that.
Yeah, I'd like to jump in on. So I really like that question by, I guess, Alex Mazursky, because I think, at least in terms of fine touch, I think that's one of the really important ways to think about this kind of problem of energy and this problem of, I mean, it's a scarcity issue. When you touch an object, you only touch it in one spot. It's not like you can have multiple sensations being generated, multiple material systems. You have one interface. So you both have to have this energy density and this density of sensations in a single intentional event. So I think the idea of having these haptic illusions or passive systems is really important, because can you put something right on the edge, and then a minimal amount of energy or a minimal amount of sensation can force something to feel quite different. So maybe I can't change the surface exactly, but maybe I'm wearing a glove and the glove has some micro patterning, and that micro patterning I can switch just enough so that when I touch that surface, it actually feels very different, just because it was right on that edge of feeling like something else. So I think our ability to rationally design this depends on our ability to understand haptic illusions, and our ability to understand how touch works on a fundamental level. Where are the opportunities where we can maximize changes in sensation with the minimal amount of energy input and the minimal amount of just material required? How can we start to have these low power systems yet still put a richness in there, and an intentional richness, right? So in this idea of communicating intent as well, if you want to create a very large difference, it's not just creating a really giant bump and a really small bump. Are there different gradations we can add on top of that, like a large fuzzy bump and then a small smooth bump? And then can we just keep going on from there? So I think that's a really important question, at least for fine touch.
I want to partially agree with you, Charles. I really like your perspective, and one of the things you said that I like a great deal is the importance of really understanding at a fundamental level how that perceptual system works, which I think is actually way more important than illusions. Like a lot of people in the field of haptics, I've spent my fair share of time trying to generate cool haptic illusions, like bumps on a flat surface. And I was excited about them until it began to dawn on me that, there are books full of really cool visual illusions, but we tend not to use them very much in a day-to-day fashion. And instead, what we tend to use is a very good understanding of how the visual system works, especially out at the periphery, right? We really understand color theory extremely well, and we make very good use of that in the way we build things like our monitors. But ultimately, the pictures that we tend to show on the monitors are pretty darn veridical. They work on our retina the same way that ordinary sight does, and the same is true by and large in the way that we interface through sound. It helps a great deal to understand, how the cochlea works, know what the critical bands are and things like this. That's really important. But at the end of the day, it's not really about illusions. It's not, when I think illusions, I think about, kind of fooling the perceptual system, taking advantage of priors and kind of making you come to the wrong conclusion, and like feeling a bump where there is no bump. So I think it's not about illusions. There's a place for them, but I think it's more about really deeply understanding how the perceptual system works, and taking advantage of that to better specify and better engineer solutions that interface to it. And I'll give you one example from our recent work. We've got this electroadhesion technology we do a lot with in our lab, which is a very, very high bandwidth way of modulating the friction between the skin and the surface. So that enables us to generate all sorts of sort of frictional, but think of it as lateral force waveforms under your finger as you're moving along a surface. And what we found is that many waveforms that you could look at a picture of the waveform and two waveforms and they look very, very different, will feel identical. And so there's this notion of metamers, things that are distinct stimuli but are perceived to be identical. It's true in vision as well as it is in touch. And understanding why there are metamers, like what is actually going on in the perceptual system that takes these two very distinct stimuli and makes them be perceived as the same. That's really valuable, I believe. I mean, once you understand that, you can begin to use that to build specifications for your hardware as well as your software, your mathematical representations. How do you want to represent texture information and things of that nature? So I'm all about understanding how that sensory system works, so that we can kind of meet it on its own terms rather than fool it.
So is the solution to be able to record touch the same way we record images and sound?
I sure wish. I wish we had that solution. It's amazing to me. Yeah, it's sort of a given that a microphone and a speaker, they kind of work in a similar way, or that we've got, cameras and displays, and that we can record what we need to display, and that there's almost a one-to-one mapping there, right? And that is not the case at all in touch. And I think, again, it gets back to touch being this bilateral thing. When you're touching the world, you're physically interacting with the world, and that means that the system that doesn't exist out there in the world today that we need in order to measure, how the world feels, probably needs to be something that's very, very much like your hands, so that it interacts in a physically similar way. Perhaps another materials challenge, I don't know, but there are robotic fingertips out there in the world today, and I've tried to take data coming from them and replay it on our devices, and basically doesn't work that well. So we clearly haven't figured it out.
And I was just going to add that I think, a lot of this discussion so far has been mostly about cutaneous feedback, but I think thinking about, kinesthetic feedback, maybe in more surgical robotic applications, more than thinking about haptic illusions, I think about sort of this, how can we use both visual information combined with some of this kinesthetic force feedback to give the sense of, that you are touching certain parts of the body, certain tissues. And as Darren was saying, it doesn't necessarily need to be perfectly realistic. You're sort of combining these different senses to get the information that you need, even if it's not sort of perfect in that sense. So again, not really thinking about illusions, but sort of this, sensory and perception.
Right. If the effect gives you the perfect outcome, then it doesn't matter how realistic it is, while not formally being an illusion. It just means something else once it's perceived.
So if I could follow on this, and I saw that there's a lot of focus on understanding basically surface energy and how people touch the world. But from this conversation, it's clear that we don't have, from a scientific perspective, a complete understanding of how humans touch. For example, several of you have already brought up this idea of we mostly touch rigid things, or things are bilateral, so we tend to impart very little energy, or the things that we touch impart very little energy. So I guess my question is this the gap? Is this the scientific knowledge gap, that we don't know in totality what percentage of things do humans touch that is hard or soft? How much energy do we put into the world? How much energy does the world put into us? Are these just is this the dark matter of haptics? And forgive my son, but he wants to join in as well in a moment.
Yeah, so if I can jump in, I really believe that there's a lot to understand about the fundamental aspects of touch, because I think at the end of the day, it's a difficult mechanics problem. So we don't feel material properties, we don't feel surface energy, we don't feel elasticity, we don't feel any of that. What we do feel are mechanical deformations on the finger. So some of the things we've shown is we can take objects with a high Young's modulus and have people tell us that they're softer. And we can routinely do this. And there's lots of examples of this. And it really comes down to the way your finger works is to feel mechanical forces. So when you're rubbing your finger across the surface, it's generating a very complex pattern of friction. And I think that's one of those societal goals to understand friction, because it's a very complex issue. I don't know if one subset of one discipline will be able to address it. But I think the ways we can get around it is, how can we kind of predict human behavior? How much is enough for us to get where we want to go? So I think I do think we do need new tools. We need new analysis methods. We need new materials to probe how touch works. And then once we know how touch works, we'll need other materials that can control those sensations on demand. So I do think there's a lot of opportunity, at least for fine touch. So I'm only really talking about this one aspect, fine touch. But if we want to really have a handle on it, I think we do need to build kind of this library of understanding around the problem, in my opinion, at least. And I'd definitely be interested to hear what other people have to say on the matter.
Tanya, what do you think for kinesthetic impedance? Is it as big a gap?
So I would say that since I focus on surface science and more of interfacial mechanics, I would say that kinesthetic is outside. I think the power requirements are very high for that. I think those are very different challenges. So, and I think maybe other people could answer those particular questions better. But at least for fine touch, there's definitely challenges in just the basics of which forces are important.
Yeah, I mean, so I have done some research in trying to understand how humans achieve the control of interaction, and there are ongoing questions. If you even think about the muscle models that we use, we control interaction with the environment relying on the intrinsic dynamic properties of muscles, that if you contract your muscle, like Laura was describing her muscle that she's developed, you increase the number of cross bridges and muscle stiffen, right? And this increase in stiffness with activation is a fundamental property of human muscles that we know has a stabilizing property, a stabilizing effect in the interaction with the environment. But if you look at the muscle models that are included in biomechanics simulation, that feature of muscle behavior is pretty complicated to include in a model. There are models from the 80s developed computational models, but to include those models into a multi-body simulation has been considered computationally taxing. And so muscle models that are included in those simulations do not even include the stiffening behavior of muscles during interaction. So there is ongoing research to improve this computationally and allow the science of interaction control. But yes, this is an ongoing area of research in the field as well.
Okay, great discussion. Question from Professor O'Malley to Ed. Given your thoughts on our need to better understand touch the way we understand vision, where should we focus our efforts? Active versus passive touch, different types of cutaneous sensations?
Hi, Marcy. Thank you for that hard question. Thankfully, we've got a whole field, and so we can distribute our efforts a bit. So to be honest, when I was talking about that sort of understanding touch the way we understand vision, I was thinking in terms of cutaneous sensation. I've spent a fair amount of time trying to program these surface haptic devices so that they feel veridical. They feel like, whatever surface you may want, a piece of denim or corduroy or writing paper or whatever you may want. And it's a very, very challenging proposition. So if that's the problem you want to solve, as I have wanted to solve, then I think it's important to focus the effort on why can't we do it today? What is missing in terms of the way that I think it was Charles, I think, said it all comes down to the forces acting on your skin, the sort of the spatially and temporally distributed forces acting on your skin. And so what in that pattern of forces is our central nervous system responding to that we are not producing, that we don't have either the actuator technology to produce, or we don't have the intelligent control algorithms to produce. So we need to understand that if we want to solve that problem. But as you know well, Marcy, the beauty of haptics is there are many, many different types of problems that we might want to solve. I mean, we might be interested in interacting with, objects in a virtual environment in a more vertical way. And so maybe that takes us into sort of a different direction. I might want to be able to provide, virtual braille on any surface. That takes me in a very different direction. I might want to be able to actually touch type, right, on a flat surface. And so now that takes me in a very different direction. So that's the beauty of our field, why we will be, gainfully employed for a while, is there's many, many different types of problems that you might want to solve. And so I don't know that I can further focus our efforts than that.
Does anybody else want to chime in?
I was just going to say, like, one of those aspects can be, so some people have proposed, like, at least one of our success for recreating vision is this idea that you can decompose visual stimuli into a combination of more basic pixels like red, green, and blue. And one of our recent works kind of showed that this perception of softness is shared between different people. So I don't know if there is kind of, and we're not the first to propose this for touch. I mean, there's this idea that are there basic ingredients of touch that can then recreate arbitrary stimulus or sensations. So at least one approach towards that could be, what other sensations would there be that are preserved between people that can be distilled down to a single sensation and then layered again with other sensations to give rise to arbitrary tactile sensations. Is that even possible? Does touch even work in a way, at least on a perceptual side, where you can combine different types of sensations? So that's one of the ways we're currently looking at it. And again, I think one of the points I'd made is it really depends on the application and what your goals are with that. But at least in terms of this kind of fine touch aspects, that's one of the things we're interested in, and other people have done work on as well.
So Marcy agrees with one of your earlier points, Charles. One thing that we are struggling with is where we need to better characterize the haptic interaction. Is it a contact mechanics issue or a tissue mechanoreceptor response issue, or do we need to get more into the neural responses to these cues? I'd like to tack on an addendum here that when I mention haptics to some people who may be like Silicon Valley futurists, they say, why are you even bothering with the peripheral nervous system when eventually we'll just be able to hack right into the brain or into the mechanoreceptors without bothering with these mediating mechanical effects at the surface of the skin. And perhaps this is not, this may be a question for the last few minutes of the session and not now, but how do you react to that? Maybe this is a good question for Yeet.
I'll just chime in real quick that what the panelists have already mentioned, that understanding what fundamentally is happening is very important, even if you're going to tap directly into the nervous system, because what signals are you going to be sending, you don't know unless you understand what is happening already. So it seems like it's not an either or, it's a both and.
I'm going to keep that response in my back pocket. Thank you. Okay, this question from the website ties into current events. Over the past year, people have been less likely to actually touch surfaces in, say, public spaces, which has greatly reduced interaction-based learning and the quality of experiences for people more dependent on touch, say, someone who reads Braille. What are some ways we can overcome this, i.e. creating and transmitting sensations in a world that is increasingly hesitant to interact with surfaces? That's a tough one. Let me broaden it a little bit to the intersection of haptic research with COVID-19. In what ways has the pandemic changed your research direction, or maybe made you apply to funding opportunities that are related maybe to COVID? And is there an intersection between haptics and the pandemic? How do you think about that?
I think we've probably all spent time thinking about that, and I've not come up with much that's very brilliant. But the one thing that I have noticed is that I've spent a lot of my career sort of on the presumption that a haptic device will never be used if I have to sort of don and doff it. And so hence our work on service haptics is all bare fingers stuff. And I'm reassessing that. We were all wearing, nylon gloves or rubber gloves there for a while. And we all are now wearing masks. And so that people can change their behavior if they view it as beneficial to them. And quite frankly, if enough other people are also changing their behavior is a truth now. And so the idea of, kind of wearable haptic devices. I mean, a watch or something like that, again, it's a behavior we're used to, but things that might be, gloves or things that might be a little bit more of a novel form factor. I'm kind of back on board thinking, okay, we can maybe do those things now. I'm not sure what the right ones are, but I'm thinking that maybe there is a place for those out there in the world.
Guess I have a couple things to add in this area. I think one thing would be, and this is not an area that I'm an expert in, but I think this area of affective touch, I think becomes important and relevant in this time where people might not be close together and near each other. And so I think that's an area where, haptics could play a role, especially in this current environment. And I think another one that I have started to think about a bit with some other people at UC San Diego is this idea of now, maybe we want to send robots into places in the world where, humans might not want to go to interact with other humans. And in that case, maybe there is an interface where we want to provide some sort of feedback to the user in the form of haptic feedback plus visual feedback that allows them to, use this robot in a more kind of intuitive, natural way of interacting with whatever, vulnerable population they may be interacting with. So I think there's a lot of interesting research directions to go from here that are relevant and related.
Yeah, I mean, I will say that personally, I have not changed, much plans for research, hoping that the situation will be temporary and we will be able to continue some of our studies that involve, older individuals. And so sure, we've been all affected by this, but and relating to I mean, that's not really what I have planned to do, but related to the people not being so inclined to touch or to interact with touch with object in the environment, you could think about substitution of those functions with devices that are instead wearable, but still can communicate information via the sense of touch, right? I do think that is a possibility. However, it is unclear how much research and development can be invested on something that is so contingent, right? Like the current situation, and is also not such a crucial, societal need, I would say, right? So it's hard to answer in a very positive way this question in a session on haptics, right? But I do think that there is opportunity for sensory substitution in that environment.
So there is oh, go ahead.
Yeah. Oh, I think we should take your suggestion about the break.
So maybe
we should take a 5-minute break because we're at the hour mark and it's dinner time for most people. 5 minutes is not enough, but it's enough for a power bar. All right, let's reconvene in 5 minutes.